This conference will now be recorded.
Well, good day, everybody. I think I can get started with the introductions as people are logging on and inputting their name in order to get into the session. This is the fourth out of five for our series. We appreciate being able to join Alex Kuripov's coastal survey series, piggybacking on their seminar over the past couple of weeks, as well as our final session occurring next Tuesday, same time and on the same link. I want to thank you all for joining us today for a few presentations about the NOPP Hurricane Coastal Impacts project. My name is Catherine Puma, Deputy Program Manager for the National Oceanographic Partnership Program Office, also known as NOPP, and I will be your MC and moderator for the session today. The NHCI project that will be discussed as part of this series is supported by the National Oceanographic Partnership Program with primary funding from the Office of Naval Research and the National Oceanographic and Atmospheric Administration. Today's discussion will include two presentations, the first of which will be given by Aap van Dongeren from Deltares in the Netherlands, and it will focus on forecasting hurricane impacts on U.S. coasts. The second presentation by Roland Romiser of the University of Miami and Stephen Beninati of the University of Massachusetts at Amherst will focus on remote sensing of hurricane impacts from space. Each presentation will last approximately 30 minutes, including a 10-minute question and answer period. For ease of discussion using this virtual format, I ask that you refrain from asking questions until the end of each presentation, where I will attempt to moderate the Q&A. I'll now hand the virtual microphone over to our first speaker to get the conversation started. Thank you, Aap, and the floor is yours.
Thank you for having me. I'll be presenting our modeling work on forecasting hurricane impacts on U.S. coast, including uncertainties. I acknowledge the NOPP program and ONR for providing the funding and my colleagues for doing the actual work. And I need to shift to the and somehow, yep, there we go. First, a quick slide for people that don't know Deltares. Deltares is a research institute in the Netherlands. We do work worldwide on water and subsoil issues. We're not a government organization, we're not a university, we're not a consultancy, but we are somewhere in between. And we are really happy to do research with US partners because we learn a lot about flooding and coastal processes that way. We're part of Team 4. Forecasting hurricanes impacts on coasts is our project name, FIX. And our goal is to do a twice daily forecast of waves, storm surge, morphological change, flooding, and also damages. This is the doodle that we used in the concept, where what we want to do is to forecast, take a hurricane track, either from GFS for non-events and COMSTC, the Navy model, when there's a hurricane event, and then drive wave models, flood models, and morphological models in order to provide those impacts. We do that for the deterministic track. We also do that in a probabilistic way by running a number of ensembles. We are now up to about 50 ensembles, but we can scale up in a cloud system to whatever number we want and however many dollars we want to spend with Amazon. So we have a model train of waves. That's a wave model called HurryWave, which we developed. It's 50 times faster than SWAN. It's a conventional model that people use, and it really helps us to do this upscaling to the ensembles. We compute the surge and the flooding using the new Sphinx model. That's also about 50 times faster than conventional models because we're using a subgrid approach. So here you see all the model domains. We compute surge along the US East Coast and the Gulf of Mexico coast, and then along from border to border from Mexico to Canada, we have individual Sphinx overland flood models. And then finally, we compute the morphological change using XSpeech, which is a 2D morphological model. You see maybe all the pink outlines. Those are a couple of hundred individual domains that we defined and built for all the sandy coasts along the US coast. So you see nothing here in Louisiana and nothing here in Big Bend, Florida. We can't run them operationally, that's too much. So what we do is we run about 5 for every operational cycle. That's what we can do with our modeling capability now, or computational capability. I'll be showing results for Hurricane Ian 2 years ago, Idalia last year, and Beryl of a couple of weeks ago. Starting off with Hurricane Ian. Hurricane Ian hit the coast of West Florida near Fort Myers, which is here. And what you see here is the flooding, and the arrows are the forecasted winds from COAMs, and that drives rain, but also overland flooding, surge. And you see here the time phase at the NOAA station where the observed and the computed water levels agree fairly well. And this is the flooding picture that we get out of it. And that's flooding. But with the flood models, we can determine other effects. So what we do is we take the flood models and combine that with footprints that we get from the National Structure database, combine that with vulnerability curves from HAZES, and then we can get heat maps of where there's the most intensity or the highest density and intensity of damages. So you see widespread damages along the Florida coast, especially around Sunnyvale and just north of Fort Myers, actually along the entire coast. And we did some verification. So if you zoom in the top right, you see individual houses, and they're painted red, up to red for from lower to higher damage. And we haven't done a really thorough analysis yet, but we did check like the areas where we see lots of red. And indeed, from aerial pictures, you see that houses are destroyed there. So it seems to do a pretty good job. What we can also do is take streets from OpenStreetMaps, and then we can compute how much inundation there was for these streets. So the legend runs from green, less than a tenth of a foot, sorry, to higher than 3 feet. That's red, so there was a large inundation, obviously, along the barrier islands, and also blues here where things were inundated. So that's something that's a product that we get out of our forecasting system. What we haven't done and can be done is to calculate disruption, so network disruption, so how and if shelters or hospitals can be reached. So we have software for that as well, but we haven't done that yet. What we also did is to compute the erosion and breaching of the barrier islands for using the XSpeech model. I showed 2 examples. One is a point here to the north of Fort Myers. So this is Sanibel Island. This is a little bit to the north. This is a natural area. People from USGS, Jenna Brown and Chris Sherwood, they took structure for motion data before and after. If you take the difference, you can compute the erosion of the barrier island. So this is the Gulf of Mexico side. The frontal part of the barrier island erodes and it deposits sediment on top of the barrier island, which is the natural process, what you would expect for a barrier island to migrate backwards. This is what X-Beach does, also red for erosion and deposition on top and over the island. So we were pretty happy with this, that we could predict this so-called Salinger regime of overwash. Things got worse more towards Sanibel. One of the things that happened was the collapse of the Sanibel Causeway, but also the breaching of the connecting islands. So this is what this is the causeway, one part of it, and another part of it in between is a sandy island, which got breached, and we predicted that with our model as well. What we saw, I don't have time for that now, but what we saw is that it initially breached during the flood surge, then the hurricane passed over. The water level in the Gulf of Mexico itself dropped pretty quickly, but all that water stored up into Sanibel Bay had to flow out again, and it scoured out this hole even further. So here you see accretion and erosion, and this is really dark red where we have a deep scour hole in where the island used to be. So that's Hurricane Ian. The next year we had a couple of hurricanes, Hurricane Lee, Hurricane Ophelia in the Atlantic. I'm showing examples for Hurricane Idalia. So it made landfall last year around August 30th in the Big Bend of Florida. Here is a snapshot of our model system. And I'm going to show results, I think only for Horseshoe Beach if you have time, but we also have it for Crystal River and also for St. Pete. What was interesting here and really nice is that even though there are lots of NDBC buoys to make comparison to, if you look at an individual track of a hurricane, it may get close to one or two of those buoys. And this is a part of the world that is pretty heavily instrumented if you compare it with other parts. But in this project, we have a team that drops drifter buoys from an airplane that flew right in front of the oncoming hurricane. So this is a picture of the Big Bend of Florida, and here you see the individual tracks. And what we did is we compared our model results with the observations of wave height and wave period, and these are so-called scatter plots. And you see that they're pretty much on the one-on-one line. That means that the modeled wave heights are pretty close to the observed wave heights. With the wave periods, we see a similar thing for the larger wave periods, but for the small wave periods, we're over predicting. And that has something to do with the wave field coming into the Gulf of Mexico. Colleague of mine made a really nice animation of this. I'll speed it up a bit. On the left, you see the wave height. On the right, you see the wave period. And the little dots are the individual drifting buoys, which have the same color. So if the circle looks transparent, we're dead on, and otherwise we're a little bit off. And here you see an instant scatter plot. So you see the wave height driven by the storm surge move onto shore and disappear. And you see how the drifters are moving in the meantime. So the drifters were placed, I would say, beautifully. Because the hurricane went right through it. And of course, this is the predicted forecasted path of the hurricane. It was a little off, actually, shifted a little bit to the west in reality. So we have to do the reanalysis, which is now just become available, and do this exercise again. But it looks, all in all, it looks good. So we have wave heights that are agreeable from our models. Then we look at water levels, and there are a lot of water level stations around the U.S. We implemented a couple in the project, but these blue markers here are all the NOAA water level stations. So we compared to 3. Blue is model results, and dashed are observations at Apalachicola, at Cedar Key, which is really close to landfall, and Clearwater Beach. And you see that we have a pretty decent match. We're off by about 10 centimeters. And given the speed that we require of our models, that's good enough for me, because then now I can do flood modeling. But before we do flood modeling, we also looked at the uncertainty in the track. So here is Here are 3 snapshots over time, 2 days out, 1 day out, and very close to landfall of the hurricane and its track. And here the little spaghetti strands are the uncertainties with 50 members of uncertainty in the hurricane. And when you compute 50 members, you can get 50 time traces, and we compare that here with the observation. So green is the observation at Cedar Key, red is our best track, and the orange is the uncertainty band. And what you see is that first the forecasted hurricane was a little bit to the west, so we didn't get the eventual observations. We didn't know the observations at the time, obviously. We're a couple of days back. But you see a large uncertainty, and that uncertainty starts to narrow as you get closer. And here you see that we're getting pretty close to what was being observed. Still, the hurricane was, in the next forecast cycles, it was shifting to the east a bit. So we got closer to the observations. And here you see that the uncertainty is quite small, but you're also very close to landfall. And if you're an emergency manager, then you have to make a decision based on uncertain information that are still a couple of days out, because you need a lead time to make any decisions. But this method can help determining that. So with the flood maps, we can make damage maps again. So here we did that for a couple of towns in the Big Bend. Luckily, it's not very heavily populated. Here is Horseshoe Beach, which is right at the point near Cedar Key. You get the flood map, and you can overlay that on top of the footprints of buildings and determine the vulnerability. And here you see individual houses that are damaged. And we corroborated that with aerial pictures from the news at that time. So here you see houses actually flooded. And same thing for Crystal River, where we got a pretty good match with what was observed. Then for this year, we already forecasted Hurricane Beryl. Hurricane Beryl came all the way from east of Barbados and traveled over Jamaica and over Yucatan, and then finally made landfall very close to Houston in near Matagorda City. And it caused widespread flooding and also disruption in the Houston area and also south. So what we see here on the top is the forecasted water level from our forecast cycle a couple days before. And green are the observations eventually. So you see the observations are pretty close to the predictions in orange. And for reference, blue is just the tide if there was no wind. We also predicted the water levels, and here this is Galveston Bay and Trinity Bay. And because of the path of the hurricane, it really pushed water up into the Trinity Bay, but also into the bayous, into Houston. And with the large rainfall, that causes a backup of the water and the flooding that you saw in the city. Coastal areas were also flooded, including parts of Galveston and coastal marshes here. So key results are that we now have a forecasting system that we can run deterministically, so for best track, but also probabilistically with ensemble members. We predict, we have a pretty fast cycle of prediction. So with speed, you would have to give some accuracy, but we're within 20 centimeters or 10 centimeters in places of the observed water levels. So that's pretty good. We're pretty happy with that, because you also have uncertainty in the elevation of the land, and with that we can make predictions of flooding, and we can make realistic flood extents and impacts. We do building damages now, but also looked at road disruption. So these water level and overland flooding forecasts can be made within an hour, and using cloud technology like an Amazon cluster, you can now also do ensembles within that period. On the right is a QR code to go to our website, and two more slides on Sphinx, our model, and Hurrywave, but that's in the background material that will be distributed. I'd like to go to our web viewer. So this is the web viewer right now. So we're running the web viewer through the whole season. It's not meant for any decision making. This is just experimental. If there's no hurricane, we're running it with GFS winds as we're doing now. This is the cycle from yesterday. And you can go and you can click on location. I think this is Charleston. It's a little slow, but you can pick up the water levels. It's a little slow coming in. Green is the observations, orange is the computation, and blue is the predicted if there's no wind. Well, there's very little wind, so these things are all pretty much on top of each other. And you can also go to flooding, which now there is no flooding. And you can also look at wave heights from our Hurrywave model. So that's the continuous forecast. And with this drop-down menu, you can go to previously run and now stored hurricanes. So Ian, Lee, Idalia, Ophelia, and Beryl. And we're going to be adding these as they come in the rest of the season, which is slated to be a very busy hurricane season. I think that's it. How am I doing for time, Catherine?
You're pretty on point. Thank you. Thank you for the presentation, interesting discussion app, as well as the web URL. We have a couple of minutes for question and answer. I would ask people to raise their hand or indicate in the chat that they have a question. We have one coming in already, but for others who are thinking of having a question, raise your hand should be as part of the reactions in GoToMeeting and might be part of a drop-down menu. But again, if you can't locate the virtual raising hand function, you can just indicate in the chat that you have a question and I can ask you to unmute. As such, we do have one question that came in through the chat. Jamie Pringle asks if you could go back to the QR code or post the URL in the chat.
Yes. And I'll post it in a chat later on as well.
And Jamie says thanks, in case you can't see the chat while you're sharing.
Yeah, I see it. You're welcome.
Christina Forbes, you can unmute and ask your question.
Hello, can you hear me?
Yes.
Okay, yes, I have a question. I work for the office, I'm the oceanographer at the Office of Search and Rescue, and we are mostly interested in surface currents for any search object or person or craft that drifts during a hurricane and we need to go and rescue them. So I was wondering if there is any plans for validating currents and also providing currents, surface currents.
So our model that we run is Sphinx. We use that at a pretty large resolution, about 200-meter resolution, which is okay if you look at water levels. And then on land, we use a subgrid method to take into account the much higher resolution bathymetry topography that we get from we got from the USGS. So we use that topography underneath our water level, and we can do it at a large resolution because the water level gradients are pretty small in flooding. That comes at a gain of speed, but it comes at when you look at currents, I think you need a much higher resolution model to do that. We can get that out of our X-Beach models that we run all along the coast. So in the nearshore area, we would be able to do that. So you would get rip currents out. We haven't looked at that. But on a larger scale, I think you need a much higher resolution model to do that properly. You're looking for people that got swept away by waves from the coast, or people that fell off a ship or something? Or what are the use
Anything.
cases? Okay.
Yeah, it's anything. We're always called to assist, and
Yeah.
so we use we have a model that does drift modeling, and so we need
Mm-hmm.
surface currents and winds
Yeah.
to determine the best location to search for those either
Yes.
people or crafts or capsized boats or
Yes.
that we need to go and rescue. It's mostly off the coast. It's not really in the inundation areas because we're not set up for that, but
Right.
just off the coast. And so
Yeah.
we normally access a lot of different models, but of course we need better models for hurricane, for hurricanes. So I was looking at this and thinking maybe, I don't know if you provide the data operationally when there is a hurricane, and if we could access those currents if you ever, if you have them, but
Yeah.
obviously, yeah.
What we have, we can share. But like I said, I think the resolution may be too low for details, so that may be tricky. Then we would need to run a higher resolution model. We've done these kinds of things for our Dutch government in the North Sea, so which is our coastal waters, but with a much higher resolution model. It can be done, but what we have from here we can provide, of course.
Okay, great,
Happy
thank
to.
you.
Yep.
Yeah.
And then just for App and Christina's awareness, there are 2 comments in the chat about this discussion, one from HS Kim and one from Martin. I won't read those out loud because they are comments rather than questions, but just pointing you to that location if you wanted to follow up on what they said. I do see that Michael Voto had a question about the recording in the chat. Thank you, Michael, for your question. This is getting recorded, and the NOPP office will post it online on the nopp.org website and YouTube channel, shooting for mid-August release. But we would be sure to highlight the release of the recordings via our social media handles and on our website. So stay tuned if you want to rewatch or send the video to colleagues later. We are
Shall I unshare?
Yes, you may. And we are a few minutes ahead of schedule, so I'll just give it a minute or two to allow anybody who's thinking to ask a question before we move on to our next speaker.
I posted the URL in the chat box, and there's also, I think that's good.
Mm-hmm.
And my colleague Marta added to my low resolution comment. We also we have a 2D model, so 2D in the horizontal, so no vertical structure. For surface currents, that's a different matter. We have a really advanced computer model called Delft3D that should be able to do what Christina was asking for, but it comes at a computational expense. So the vertical structure is also very important, of course. Yeah.
Well, thank you, everyone. I think that it for the Q&A session for our first speaker. I will now hand the session on to our second talk of the day. Thank you, Roland and Stephen. You both have the floor.
Yeah, thank you, and good afternoon. Welcome to our presentation. So this is about the remote sensing part of the project, and the presenters are me and Stephen Beninati from the University of Massachusetts Amherst. And so this is task 2 of the project, and this is a little overview of what we can do with remote sensing techniques. We can certainly derive wind and wave fields from SAR images while the hurricanes are over water. This has been done for many years. We have a lot of experience with it. We can also see water lines in flooded areas in radar images before and after the hurricane landfall, and we will talk about that today. And a new aspect that we didn't have so much experience with is land topography before and after hurricane landfalls, which we do with radar grammetry. And I think most of the presentation will be about this radar grammetry technique. So I already said that we use SAR, synthetic aperture radar, which is an active microwave instrument that can make high resolution images, and it can look through clouds, and it's independent of daylight. So we can take images even during the hurricane, and we can look through the clouds and everything. We can always take images when satellites come over. And the radar also allows us to do some topography measurements and to measure the surface roughness and some other things that you would not be able to do with optical imagery. But of course, when there are clouds and stuff like that, or at night, you cannot do any optical imaging. So we don't have these problems with the radar. The two teams working on this are these teams here. Our team at the University of Miami with me and Hans Graeber and Mike Caruso, and our PhD student Victoria Pizzini. And we are working with Airbus Defence and Space as our industry partner, who provide the satellite images and radar grammetry products. And we have the other team here of Stephen Fraser and his PhD student Stephen Beninati at the University of Massachusetts Amherst. And Steve Fraser is in the audience today, I think, but he is on vacation. That's why Stephen Beninati is giving the presentation on that part. And Stephen and I gave very similar presentations last week at the IGARS conference in Athens. And it turned out that Stephen has some more fundamental slides in his presentation that explain how some things work. My presentation was a little bit more on higher level results. So we decided it makes more sense when Stephen begins with his presentation now and explains everything in detail, and then I continue with some results that we obtained at the University of Miami. So I will now switch to the next slide, which is Stephen's title slide. I will continue to run the slides from here, and you will now do the talking, right?
Okay. Yep. So as Roland mentioned, we've been working with an industry partner called Capella Space, who runs a high-resolution synthetic aperture radar satellite constellation. So I'm going to talk a little bit about some work that myself and my co-authors have performed with this data. Next slide, please. Mainly, I'm going to focus on two tasks that we've focused on here at the University of Massachusetts: waterline detection using SAR and topographic reconstruction using SAR. Next slide, please, and you can also go through that one quickly. It's just the title slide. I'm going to talk about waterline detection using SAR. So what we rely on when we do waterline detection with SAR is the different appearances of water and land in SAR images. Namely, land exhibits what we call a diffuse scattering. So it's like if you look at a wall, I think the slide might have advanced one more than it was supposed to. There we go. Okay. Where it doesn't matter what viewing direction you look at, the brightness is relatively the same. Whereas water, calm water especially, appears as a specular scatterer, so it appears basically like a mirrored surface, which means that when we look at it with our radar, we get different brightness levels from the two. specifically in images with a high incidence angle. So incidence angle is the angle from vertical to the view direction of our radar. Water generally appears very dark and land appears brighter. And then in images with a low incidence angle, water can appear very bright and land often appears darker than the water in that case. So what we can do is we can separate land and water surfaces based on pixel intensity. Next slide, please. We detect them the waterline, knowing the contrast, by finding pixels with a high gradient, which means a large difference in brightness between neighboring pixels. We also call this an edge. And our edge detection can be further improved by filtering the edges using a digital elevation model. So what you can see here is an image of Madeira Beach, Florida, near the Seminole/Tampa Bay area, where we have a very nice dark, smooth water surface appearing in the image, along with a gray land area consisting of a lot of buildings. These buildings will produce a lot of false positives unless we do what I mentioned, which is filter them with a digital elevation model. So if we know roughly the height range that we're expecting our water line to be in, we can set a limit. And really what we do in this is a couple meters of limit. So within about a 3-meter range, we find the water line. Next slide, please. And that's what you can see on the image to the right. Then, once we have this water line, we can estimate the mean water level in the area if we mask a digital elevation model with our SAR water line. And that's what you can see in the imagery here. We take a simple classification of water line versus not water line pixels, which is that black and white image. And then we overlay it over the NOAA continuously updated digital elevation model. And we achieve the result shown here, where you can now see it's a colored gradient of what heights the different water lines we've detected are at. Next slide, please. We applied this method to this Madeira Beach location during Hurricane Ian in 2022. Hurricane Ian made landfall near Fort Myers, Florida, which is a little bit south of Tampa, but we acquired imagery at Tampa Bay. What this allowed us to do was capture the set down that was observable at Tampa Bay during the hurricane. And you can see it, I guess you can't see it that well in those SAR images. But what we did was we detected the water line in each of 3 SAR images over the course of that hurricane landfall on the 27th of September, the 28th of September, and then a few days later on the 1st of October. We map them to the corresponding DEM heights, and that allows us to estimate the water level at the area that we're looking at. We have a time series from Madeira Beach, Florida, and then we have a single image from Clearwater, Florida, taken on the 28th of September. Next slide, please. The plot here shows the mean water level based on tide gauges versus the mean water level we've calculated using the SAR images at our test sites. The blue line indicates the tide gauge at Clearwater, Florida, while the orange line indicates the tide gauge at near Tampa Bay, Florida. The green dots are our time series from Madeira Beach, and the red dot is from Clearwater. So the green dots go with the orange line, and the red dot goes with the blue line. As you can see, for the orange lines at Tampa, we seem to be getting pretty good matches between our SAR-derived heights and the actual mean water level at the time. At Clearwater, we seem to have underestimated it slightly, but that's the kind of results that we can achieve with this waterline detection method. Next slide, please. Next, I'm going to talk about topographic reconstruction using SAR. Some of you might be familiar with or have heard of SAR interferometry as a method for topographic reconstruction. In this method, a differential phase of a signal received at 2 antennas is converted to a height value. This method is very high resolution, but it has the drawback of requiring a very precise imaging geometry. That baseline there in my image has to be pretty well controlled in order to extract good height data. With a satellite constellation like the one we're using with Capella, this isn't achievable for most looks. So in order to be able to apply our method to rapid collects from any look direction, we decided to use a second approach called stereogrammetry. This method is very similar to optical photogrammetry, where you take pictures of a scene from two different viewing directions, and then the differences in the location of objects in the scene tell you something about how far away they are from your imaging cameras. In this case, our imaging camera is a radar, and the technical details of how the pixels move are a little different. They move based on distance to the radar. So you can see here a image of two satellites looking in the same direction at the same point on the ground at two slightly different incidence angles at a surface above what we call the image projection plane, which is just the assumed height of the surface that we're looking at. Pixels that are not at this assumed height will wind up in a slightly different location in the final image than their actual true ground location. When you have two images, you can compare how far the same pixel has moved in two images, and we call that the disparity. And then we derive our height from the disparity in the imaging geometry. This method is more tolerant to varying the image geometry than the interferometric method, which is why we've chosen it for our data. Next slide, please. So as I mentioned, our topographic height estimation is based on this disparity metric, which is the difference between corresponding pixels in the two images. Two pixels correspond if they are of the same object. And the way that we figure out whether two pixels are looking at the same object is by minimizing a matching cost function that basically assigns a value to every pixel in each of the two images in a stereo pair. And then we slide the two images across each other and compare those pixel values. And when the pixel values are close to each other, that's a good match and corresponding pixels. You can see how that works in the animation shown on this slide, where as we slide one image over the other, or the metric that we're using for the image over the other, you can see this dark region start to go across the bottom of the image. That indicates a good pixel match. So you'll see as it moves slowly from one side to the other, different pixels match well. From this, we're able to compute what's called a disparity map, which tells us how far away corresponding pixels are in different parts of the image, and then we can calculate the height from that disparity and the imaging geometry. Next slide, please. We applied this method at two sites, one at Monterey, California, and one at Panama Beach, Florida. I'm going to show the Monterey results first, which are at a 2.45 meter ground resolution. And based on that ground resolution and our imaging geometry, we have a theoretical vertical resolution of 1.2 meters. And you can see the two SAR images we used, as well as an optical image of our target area, which is primarily golf courses. It's about a 30-meter relief between the coast and the highest point of land in that image. Next slide, please. Shown at the top is the geocoded output of our radar grammetry method compared to the NOAA continuously updated digital elevation model. And then you can see a scatter plot showing the differences between those two. And you can see that they achieve a pretty good agreement. As I mentioned, our theoretical vertical resolution of our radar grammetry is 1.2 meters. And that's reflected in the fact that the majority of the points in the scatter plot are clustered in kind of steps as you go up the scatter plot. There was some interpolation done, and that's why it's not entirely discrete steps. Next slide, please. We also applied our algorithm to a site near Panama City, Florida, with SAR images that had a slightly larger ground resolution and a slightly lower theoretical vertical resolution of 4.7 meters and 3.3 meters respectively. This site is also much lower topographic relief than the previous one, and you'll see that in the next slide. Next slide, please. So here's our results from Panama City. These have been, again, interpolated to a geocoded output. So this is like in map coordinates. In this case, there was a slight bias to our algorithm that we had to correct based on the mean error. But then we've otherwise corrected it for the distortions of height in the XY coordinates, and we compare it again to the continuously updated digital elevation model. You can see the relief in this region only spans about 8 meters as opposed to the 30 at the previous site, but we still achieve good agreement. Next slide, please. So in conclusion, SAR is an effective tool for monitoring coastlines. Water lines are observable when we have a high contrast, and stereo imaging is usable for topographic reconstruction from these SAR constellations. You can also see how we can integrate other DEM products to extend the applications of SAR, for example, in determining that mean water level during the hurricane. Further work includes investigating feature size limits for topographic reconstruction, improving detection of shoreline and cluttered areas, and further integration of SAR-derived products with digital elevation models. And at this point, I'll turn it over to Roland to finish out.
Yes, thank you. And so somehow your slides on 2 occasions here advanced themselves. That was not me pushing the wrong button, but they somehow advanced themselves. There must be something in the PowerPoint file that advanced them without my input. Yeah, so now I will talk about what we are doing for the project in Miami, which is very similar, but it's a different team and different data from different satellites. So we also use this Hurricane Ian Tampa Bay example here as our main example, because that's the best hurricane we have had so far with the most images acquired. And here's a pair of images from 2 Terrasat X-type satellites. Here first the PAS-1 satellite here on September 27, 2022, and then the following day, almost exactly 24 hours later, the TDX-1 satellite took another image with 2 very different incidence angles. And then the same was obtained here after the hurricane landfall, here first with the PAS satellite again, and then in this case 2 days later with the TDX satellite. And so these are the 2 pairs that were used for radar grammetry. In this case, the radar grammetry was done by Airbus Defence and Space with their existing algorithm that had already been used for some other projects. So it was supposed to be good. Here is a zoom in. You see St. Petersburg there in the SAR intensity image. And this is the corresponding elevation map they came up with. This was the initial result. Then on the left, now you see the corresponding reference topography from the LiDAR measurements from the QDEM data set. And you see this doesn't match perfectly. So this was the initial stuff we got. Of course, we assume that the LiDAR data are correct. And here is the second result from the second image pair, very similar. Doesn't look too bad, but it doesn't look exactly like the LiDAR data. And if you compare this in a scatter plot for the first pair, here on the left, you see that the radar grammetry heights are a little too high. But what we did now, we fitted a polynomial here to this distribution. And from the polynomial, from the red curve there, you can see how the height should be corrected. So we made the simple mapping function here to correct the heights. And if we apply these relatively simple corrections to our radar grammetry heights, our scatter plot begins to look like this. And in the map, this makes the following. Oh yeah, no, yeah, here, again, the same for the second image pair, same fit, correction function, and improved scatter plot. And then when we look at this again on the map, reference topography and the initial result here from the first pair, now it will fade over to the tuned result with the tuned heights, and you see this looks much better. And the same here for the second pair. This was the initial result from the Airbus guys. This is the tuned result. And I think here I have a zoom in. Yeah, so this is just to show the resolution that we get here. You see some structures there of streets and buildings, and you can fade this over to the underlying optical image in Google Earth there, and you see we don't resolve every little house, but we resolve the bigger buildings and the bigger streets. And this looks actually a little better in the actual data than it looks here in this Google Earth representation, which smoothes everything a little more than it really is. So we can say we can resolve streets and bigger buildings and blocks of buildings. So maybe, I don't know, 100 meters or so spatial resolution. And we are still working to see how accurately we can measure the actual height of the buildings. Here, a comparison between the two pairs. Here, this is how they compare from the pair acquired before the overpass and after the overpass of the hurricane, which didn't really do much damage here in the St. Petersburg area, so that there shouldn't really be a big difference between the two pairs. And so on the left, that's before tuning, on the right, that's after tuning, and you see that the tuned data now agree well with each other. So that's our radagrammetry result. Now, this was done with the original algorithm. In the meantime, the Airbus people have implemented a new algorithm that produces data at a higher spatial resolution, but also with a little more noise. I don't have new results from the new algorithm here in this presentation, but we are working on that, and we may be able to do all of this even better than with this old algorithm in the next few weeks. Now, here's something else. Stephen already explained how the waterline extraction works. We are doing the same here in Miami. This is now from the Cosmos SkyMed image, not from TerraSat X. Cosmos SkyMed is an Italian SAR satellite system. And my colleague Mike Caruso applied an algorithm very similar to the one described by Stephen, which came up with these water lines here. And then there was another image. Yeah, this is just a water line on the Google Earth background. And there was another image from the Finnish Ice Eye SAR constellation, taken actually a few hours earlier here on the same day, which produced these water lines. Now you can zoom in to this area here with a lot of islands and little town there. These are the Ice Eye water lines. These are the Cosmos SkyMed water lines. You see they are quite different at the two different times of the day. And here we could do the same kind of analysis that Stephen presented to see how the water levels were different at the two different times. And then finally, I said this is standard stuff, but it's still interesting. We have a bunch of SAR images here from Hurricane Lee from last September 2023, from which Mike Caruso derived the wind fields with an algorithm that uses the SAR image intensities combined with a boundary layer model to correct the wind field to make sense physically. Here is the result he got for this first image here. And this is the corresponding COAMS wind field with the same color coding. You see the agreement is relatively good, and now one could analyze what is wrong here. Is the SAR algorithm wrong, or is the model wrong? Then this will continue with 2 or 3 more examples here taken a little later while the hurricane was moving along. So this is the next image, again a pretty good agreement here. And another one, lower left is the original image, then Mike Caruso's wind field and the COAMS wind field. And yeah, one more even, there it is. Bigger pattern there now. And again, relatively good agreement, at least quantitatively. Maybe the size of the hurricane eye is a little different now. So that's what we are doing in a quick overview summary. So we utilize TerraSat X radagrammetry for rapid mapping of topographic changes. That's our main business, where we spend most of our time within this project. We have shown that we can acquire suitable data, the image pairs, within 24 to 48 hours. In future, this may be even faster with the constellations like Capella that have a lot more satellites. Our radar-grammetry products are in good agreement with the LiDAR reference topography after some simple tuning. Spatial resolution, small-scale accuracy still needs to be determined, especially when we switch to the new algorithm now. But we know we can see streets and larger buildings, so that's about what you can expect here. This should be good enough to see large dunes that are changing their shape, or bigger blocks of buildings that are changing their shape due to the hurricane landfall. And we also made these waterline and flooded area products and the wind fields that I showed you briefly. And so, yeah, so this is what we do in Miami, very similar to what they do in Amherst. And that's the end of my part of the presentation and of the whole presentation.
Thank you, both Roland and Stephen, for the presentation. Good discussion. We have just a few minutes for Q&A, so please, participants, either raise your hand or put in the chat any questions that you might have for our speakers. App, I believe a question for you came in through the chat from Ali Abdelharim, asking if the Hurry Wave model is available to the public. They wanted to try and find it online.
Okay, not yet. We need to release it still, so it's coming.
Thank you, thank you. Just checking the participants, see if we have anyone raising their hand.
Yeah, no, they are all leaving. Come on, people, we need at least 2 questions. One from me, one for Stephen.
I can ask one if I'm Christina again. I can ask one if regarding the wind fields. Are those so those would be real time, I guess. The ones you're providing are real time. The RCM, is that from? Did I understand that correctly? Yeah.
So the RCM here is the RadarSat constellation mission. That's a Canadian satellite now. So we have a broader variety of different satellites here that we can access. So this image was acquired by that Canadian satellite, and the wind field, of course, represents the wind field at the time of the image acquisition. Regarding real time, so we don't have this instantaneously. We first need to receive the image and process the image and apply the wind algorithm. I'm not sure how long that takes. Probably, I would say a few hours after the image acquisition, we would have that wind.
Okay, and those winds are 10-meter winds, is that?
Yes. Yeah, it's supposed to be U10, yes. And that's not shown here in the picture, but it has directions and wind speeds. And I could talk about that for an hour, how the wind directions are retrieved. It's a complicated process, but our wind fields come with directions and magnitudes.
And are those available like during a hurricane?
Yeah, they should. So technically, we produce them as soon as we have the images, and we can make them available to our project team. I must say, last year I saw most of them only when Mike Caruso presented them at our final meeting of the year. But in principle, this is something that can be done relatively quickly. And at least within our project team, it can be made available quickly. This is not operational public stuff like some products from NASA or from the European Space Agency. But technically this could be made available very quickly, and the rest is negotiation and so on. I don't know who is allowed to get this or who is not allowed.
Okay. Yeah, because when we access models, in general, either ocean models or atmospheric models, the real-time observations are very important. Sometimes we have a couple of models that don't match, and so we need to figure out which one is the closest to the real observation. So it's really good to have something to compare with, which model to use for our forecast for search and rescue. So that's what I was thinking.
And yeah, and as you can see, this is pretty high resolution here. Of course, you have the wind scatterometers that make wind fields every day. At the moment, mostly the European ones, and you can get them from NOAA, but they are not at this high spatial resolution. And with the SAR, you really see details of the wind field and where the eye walls are and everything. Now, of course, this is not an operational thing that's acquired automatically. We have to order these images specifically to obtain them, and they don't come necessarily on a regular basis every few hours or so. So that could make it difficult to make use of these wind fields and assimilate them into a model or so. But yeah, in principle, the SAR can really produce very nice high resolution wind fields. The coverage is, I don't know how wide these radar set constellation images are, but in principle, this could be like 400 kilometers wide and even a little longer than that. So pretty good large area that can cover a lot of the hurricane if you order it correctly and you look at the right place. Of course, you have to predict a little bit when you order the acquisition where the hurricane eye will be. You have to do that 1 day in advance or so to catch it there.
Right. No, it's very nice. It's very nice, high resolution. Yeah, that's very nice. Thanks for showing this and doing all this work.
Yeah, as I said, this is not our main effort in this project, but yeah, it's really a nice product, and we have come a long way producing something like this. When I started to work here 16 years ago, we had the first project on hurricanes that I got involved in, where we still figured out some basic things. Now this is all more or less automatic here with combination with the boundary layer model and everything, and you get these really good wind fields.
It's very nice and very important, I think. So, yeah.
Well, thank you. Thank you, everybody. We are a minute or two over for our allotted time today. We really appreciate it, everybody's participation and attendance and questions. Thank you especially to our speakers today, all three of you. Great discussion, great presentations. This is a part of the NOPP Hurricane Coastal Impacts Forum. It is a multi-part series. This concludes the 4th out of 5, so we have one more. Please tune in next Tuesday, same time, and via the same GoToMeeting link for that presentation, and we look forward to it. Thank you, everybody, for attending, and I hope you have a great remainder of your day.
Bye-bye.
Yeah, thank you for coming to our presentations.
Thank you.